Thank you very much, Rohan. Okay, we have a first question for you from Gunnar Wolf. Gunnar, yeah, okay, go ahead. Oh, we still can't hear you. You're unmuted, but for some reason your microphone volume seems to be down. Now it's all garbled. Rohan, I assume you cannot hear him either.
Sorry, I can't hear.
Okay, I'm going to mute you, Gunnar. You can try to figure it out while I ask another question from the Slack. Okay, so let's go to the Slack questions first then. The first one that I see here is by Suvik Banerjee from, who's a software engineer at Apple. He says, YNFS looks great. What settings were used for ext4 DAX? Specifically, he's wondering how performance compares to ext4 DAX with the block size set to 2 megabytes.
Yeah, so thank you for the question. It's a great question. Basically, we talk a bit about this in the paper, but it's not there in the presentation. Intel actually recommends to set the block size of ext4 DAX and XFS DAX to 2 megabytes to reliably get huge pages for the memory mapped applications. While this gets good performance for the memory mapped applications, it causes like enormous space amplification for other applications with small files. Like when you have file servers or kernel compilation and applications like that, when you have like 4 kilobyte files, you end up using 2 megabyte space on persistent memory. In fact, when we run our aging tool on ext4 DAX with 2 megabyte block size, we find out that it runs out of space even for a small number of small files. And so that is why in YNFS, we try to achieve like the best of both worlds, where we try to avoid space amplification for applications with small files and also give huge pages for applications that require huge pages with large files.
Mm-hmm. All right, thank you very much. Gunnar typed his question into the chat. Gunnar, do you want to try again first, or do you think it's not going to be fixed? I can just read out the question. No, sorry, it's not working. Okay, I'm going to read it for you. So Gunnar says that the presentation mentioned in the beginning that YNFS is targeted at non-volatile memory systems due to their high bandwidth. It seems that it would also be usable for regular SSDs or even hard disk drives. Have you tested this? And is there a strong reason to limit YNFS just to NVM?
Right, so I believe that YNFS only will work on persistent memory or non-volatile memory. And the main reason behind that is that YNFS targets to get huge pages for memory mapped applications. And in the case of hard disks and SSDs, when you try to memory map a file, the data is copied to DRAM and then it is mapped to user space. And so file systems don't really have control over whether you can get huge pages or not for these other storage media. But for persistent memory, you have a feature called DAX, with which you can directly map persistent memory into user space. And this is when file systems allocations can actually play an important role of whether you can get huge pages or not.
All right. Thanks very much. Let me see if there's any other hands up. Can't see, so let's take another question from Slack. Qing Wang from Tsinghua University is asking if persistent memory is accessed remotely via RDMA, can YNFS improve the performance of remote persistent memory due to smaller page mapping in the NIC's SRAM?
Yeah, this is actually an interesting future direction, I would say, for YNFS. We currently focus on local persistent memory, but I think it will definitely be able to improve performance for remote persistent memory, because if it is able to reliably provide huge pages for the RDMA pinned memory, then I think the NIC's SRAM can cache the page mappings, and that would improve performance for remote persistent memory as well. I'm excited to try it out later.
Sounds reasonable, yes. Okay, next one is from Chloe Alverdi from the National Technical University of Athens. In fact, it is multiple questions. Let's try the first. The question is, the paper very nicely studies how metadata fragmentations PM over aging or gets fragmented in persistent memory over agent. But did you perhaps study the effect of append operations? So for example, a file ends up being large enough for a huge page, but by being appended to in smaller portions, it might get kind of smaller chunks that get added at the end. Your allocator will treat such a case from the pool of small or from the larger extents?
Yeah, this is a very nice question, and an interesting thing that we also had to like figure out in YNFS. So basically, from my understanding, the question is that if we append a file through small append operations and then it reaches to a large size and we try to map the file, then do we get huge pages or not? The answer is no. Initially, we don't get huge pages because the allocator thinks that it is not a memory mapped file and allocates it from the small pool. But YNFS has a policy called reactive rewriting of files. So what that basically does is that when a file grows in this way and is mispredicted by the allocator, when you perform a memory map, the first memory map will not get huge pages, but a background thread then tries to rewrite the file in huge page extents, because now we know that this file is memory map friendly. So any future maps that are done for that file will get huge pages.
Mm-hmm. Did you put in some measurements into the paper about the overheads of doing that in the background?
We talk a bit about how much bandwidth it takes for rewriting the file along with the concurrent threads that run for other applications, and that is a non-trivial amount. So if I remember correctly, in our experiment, we saw that there was around 20 to 25% drop in the bandwidth experienced by some other micro benchmark that purely did persistent memory accesses while the rewriting was going on. And that is also one reason why we try to actively preserve huge pages and not defrag or not use defragmentation tools and something like that. Mm-hmm. But having said that, this case never occurred for any real applications. All the real memory mapped applications, you use large allocations and then memory map. They never append in small bits and then memory map later on.
Mm-hmm. So there's a follow-on question that I'm going to paraphrase. This similar problem will occur when you have multiple NUMA nodes, since the memories are going to be separate, right? You could have fragmentation that starts to creep in as an application is first started on one NUMA node, but then later moved to another NUMA node by the operating system scheduler. What do you do in these cases? Will the file end up being scattered over multiple NUMA nodes? Are you going to defragment in the background also across NUMA nodes?
No. So in YNFS, what we do is that whenever a file is created by some application, we try to find out which is the NUMA node that contains the most number of free space and huge pages, and we use some policy there in order to determine which NUMA node to give that file. And then we maintain a map in YNFS which stores that process ID X is going to access data from NUMA node 1 or 0 or 2. And then for all the future files that are created by that process ID X, we try to use the NUMA node that we initially used. So we avoid scattering files across multiple NUMA nodes in YNFS. And if we see that threads of that process X are if the threads are from a remote NUMA node, then we migrate those threads to the NUMA node, which contains the files of the process.
Mm-hmm. Right. So you're trying in some sense to keep the compute close to the data rather than moving data around excessively. That makes sense. We're out of time already, unfortunately. So I'm going to go on to the next paper. Thanks very much, Rohan.
Thank you.
Okay, and our third and final system today has no name, but maybe we can change that during the session. It's presented by Jing Liu, a sixth-year PhD student at the University of Wisconsin at Madison. Sigops, please roll the video.
Okay, thanks for the talk. Rohan, now you can turn on your camera and microphone. Okay, hi. So Rohan's ready to take the questions. So let's kick off with the questions on in the Slack channel. So it's Jingwei from SGTU. He asked, in age scenario, some cores may use up their allocated free space. So if that happens, can they do cross CPU allocation?
Thank you for a question. So yes, it is true that some cores may use up their allocated free space when aged. And in this case, YNFS does use cross-core allocations. So basically, YNFS looks at the allocation request. And if the allocation request is a large request of 2 megabytes or greater, then YNFS uses the free space from the core that has the maximum number of free 2 MB aligned extents. And small allocation requests are satisfied from the core that has maximum number of holes. So this is how YNFS is able to perform cross-core allocations.
Okay, so I have a follow-up question. So for the cross CPU allocation, will that affect the performance of allocation?
Yes, it does affect the performance of allocations because you have to scan through the other cores in order to find the correct core, and that might also lead to some kind of locking problems where if there is an allocation request for that same core. But in the applications that we studied, even multi-thread, we did not see any visible performance degradations due to this.
Okay, thanks. So June Park. So what's your question?
Can you hear me?
Yes.
Yeah.
Hello, I'm Jonghyuk Park from Sungkyunkwan University. It is really interesting talk, and also it is really interesting because we use persistent memory as storage, but the phenomenon is really similar to memory fragmentation. Do you think we need to design a new way of page tables, such as like extents-based or something?
Yeah, thanks for your interesting question. So I think one difference where persistent memory and DRAM based allocations differ is that persistent memory allocations are persistent and you have to be more careful when allocating because it will be there for long term rather than DRAM, which ends when the process ends. So I think that we can use something like extent-based page tables for getting fewer page faults, but I'm not completely aware of the integral details of how this will affect in the DRAM case, because as I mentioned, the allocations are long-term versus short-term.
Also, like similarly, do you think various sized huge pages, because huge pages support only 2 megabyte and 1 gigabyte currently, I guess. And do you think various sized huge pages and allocation methods, such as like body allocator stuff, could improve performance?
So the problem is that today there's a hardware limitation because of which the huge pages are 2 megabytes or 1 gigabyte in size. Basically, in your page table hierarchy, you have 512 4 kilobyte entries mapping to 1 2 megabyte entry. And that is why you have huge pages of 2 megabytes and similarly 1 gigabyte. So having a body allocator and different page sizes of 8 KB, 16 KB, I don't think that will reduce the page faults unless there's some hardware change.
So we need to entirely change the page table structure, right? To support such stuff and to be efficient.
Yes.
And also, if I have time, I want to ask more questions because this is really interesting work. Yeah. Do you think defragmentation tool is needed for PM file systems and it can be beneficial?
So I definitely think that defragmentation will help in memory mapped applications. It does not help in the other system call applications like file bench or any other applications because the random access performance of persistent memory is as good as sequential across blocks. So for memory mapped application, definitely defragmentation is useful, but we have to keep in mind that defragmentation utilities also take up available bandwidth of persistent memory, which is already limited. And in the case of memory mapped applications, the applications themselves try to access persistent memory from user space, and they try to get the maximum bandwidth out of the hardware. So you have to be careful enough to not hurt these application performances while performing defragmentation, which is why we kind of promote more proactive approaches to avoid fragmentation.
Oh, finally, I think PM and NUMA architecture cannot be decoupled actually. So do you have any quantitative data of NUMA effects on PM file systems, not only YNFS, but other file systems?
Yeah, I think NUMA has great performance effects on persistent memory file systems, because in terms of persistent memory, what we have observed and what others have also reported is that writes to remote NUMA nodes are much slower than writes to local NUMA nodes. And that is why your persistent memory file system, if it is not aware of the underlying NUMA hierarchy and it just considers persistent memory as a range of bytes, then you can get a lot of performance degradation from accessing remote NUMA nodes. So we believe that persistent memory file systems should be aware of this NUMA hierarchy. And for especially writes, persistent memory file systems should make NUMA aware writes by either moving compute near to the data or else migrating data near to the compute.
But the problem is it's really
So due to time limits, maybe we need to give time to some other questions.
yeah, I will
okay,
ask about it in Slack.
Okay.
Thank you so much.
Okay, so we have another question in the Slack channel. So it's Vijay from SGTU. He asked, why do you choose to implement YFS based on PMFS? Is it difficult to convert log structure file systems such as NOAA and Strata to hugepage-aware? And if yes, why?
Yeah, so this is a great question. We had to think through this when also designing YNFS. So one main advantage of PMFS is that its on-disk layout aligns with the ideology of YNFS. So PMFS basically is a journaling file system, and all its metadata is contained into either a journal or the inode tables, and there is no other fragmentation that goes on. As opposed to this, in terms of NOVA has a per file log which stores write entries and directory entries for directories, and that gives high scalability to NOVA at the cost of fragmentation. So we wanted to design a file system from ground up that is suitable for huge pages, and so that is why we thought that journaling is better than log structured design. And that is why we went ahead with PMFS as a design. And also PMFS is a very thin file system on which we could easily add our own optimizations and our own contributions to make it huge page aware and age friendly.
Okay, thank you.
Similar is the case with Strata, because Strata is also kind of a log structured file system where you have per process logs, which tend to if you have small files combined with large files, the small files will misalign the free space, and then the large files will not be aligned in huge page extents and cause it to fragment. So to get more page faults. So yeah, that is what our
okay, thank you. So a short